In this part of the review video, I'm going to be looking at some clock problems. So we start out with 8 o'clock. 8 o'clock should be real quick because we don't have to worry about the hour hand moving anywhere. It's pointing exactly at the 8. The minute hand is exactly at the 12. So a circle has 360 degrees. If you count, there are 12 intervals between the numbers, which means there's 30 degrees between each number on the clock. So from 8 to 9 is 30, 9 to 10 is 30, 10 to 11 is 30, 11 to 12 is 30. That's 4 30s. 4 times 30 is 120 degrees. All that's going on in that first one, all right? The next one's 7:50. Okay, if you don't know how to use a clock, the hour hand points at the hour, so it's pointing at 7. Each number on the clock represents 5 minutes, so the minute hand is the long hand, and we're 10 5s in the hour, so that's 7:50. So the way I approach these problems is I act like the hand is pointing at exactly the 7 and exactly the 10. That's not how it works, but then I adjust later. So from 7 to 8, that's 30 degrees. From 8 to 9, that's 30 degrees. And from 9 to 10, that's 30, okay? 3 times 30 is 90 degrees if those hands were pointing exactly where we think they are. But they're really not, okay? The hour hand moves throughout the hour, okay? So the hour hand has moved some part of the distance from the 7 to the 8, and we're trying to figure that out. Well, there's a total of 30 degrees between the 7 and the 8, okay? We just need to find out what fractional part of the hour are we done with. A fraction is a part over a whole, right? In this particular case, we are 50 minutes of the way through an hour that has 60 minutes, which is 5/6 of an hour. So that means that the hour hand has moved 5/6 of the way from the 7 to the 8. So I want to take 5/6 of that 30 degrees between the 7 and the 8, and I want to figure out, okay, it's moved 5/6 of that way. What is that? Well, if you multiply that out, you end up getting 25 degrees. Okay, so this is telling me that the hour hand has moved 25 degrees from the 7 to the 8, okay? I draw arrows in here because that reminds me that that angle is smaller than the original 90-degree angle. Okay, that angle is closing as that hour hand comes in toward the minute hand. And by the way, it's not always that way. So you got to look at the problem and see, is that hour hand getting closer to the minute hand? If so, the angle's getting smaller and you need to subtract. If it's moving away from the minute hand, then you need to have your angle increasing and you would add. But yeah, in this case, we're going to take that 90 degrees, subtract that 25 degrees, and we end up with a 65-degree angle. All right? Next one is 3:30. Okay, so again, in a perfect universe, we've got a hand pointing exactly at the 3 and exactly at the 6. And 3 times 30 is 90 degrees, okay? But that hour hand is moving between the 3 and the 4. It's going to move half of the way between the 3 and the 4. And by the way, this one's simple enough. A lot of you might just be able to say, oh, it goes half of the 30 degrees between the 3 and the 4. That's just 15. But if you want to take 1/2 of 30, if you want to do it the same way as the other ones, we get 15. Same kind of thing here. You have to decide, as that hour hand moves from the 3 to the 4, is the angle getting bigger or is the angle getting smaller? And once again, that hour hand is closing in on the other hand. So the angle is getting smaller, which means we need to take that 15 away from the 90, which is going to leave us with a 75-degree angle. And our final one, 5:40. So you've got the hour hand pointing at the 5. The minute hand is pointing at the 8. 8 times 5 is 40. Again, if there was everything exactly where we want it, we could take 3 times 30 and get 90 degrees. However, this hour hand has moved a fractional part of the way between the 5 and the 6, okay? We are 40 minutes into the hour. The hour has 60 minutes. So we are 2/3 of the way into the hour, which means this hand has moved 2/3 of the way from the 5 to the 6. It's moved 2/3 of 30 degrees, which is 20 degrees. So it has moved 20 degrees this direction. Once again, that's going to close out that angle. And we can subtract 20 from 90 and we end up getting 70, okay? Be careful because you can add or, this can be done using either adding or subtracting. And it just so happens that all the examples on this sheet are ones that involve subtracting, but they don't have to be, okay? Let's jump over to the last page. I think I'm going to do the if-then statements in a separate one. We've got this one triangle inequality here. We can do this as part of the other problems. All right, triangle inequality. So we got a triangle here. We got a side length of 7 and 4. The length of BC must be between what two values? So basically, kind of imagine that those two sides that were given, imagine that's just kind of open. And we know this is 4 and this is 7. And we're imagining like, okay, how big can this third side get to be? How small could I make that third side? Well, the bigger you open up this angle, the larger that third side of that triangle is going to end up being. You get, stuff that looks like this, for example, okay? So you can keep opening it and keep opening it and keep opening it, and it quits being a triangle at the moment that those two segments are laying flat, okay? And if those two segments were laying flat, the segment that would kind of connect those would be 4 plus 7. It would be 11 units, okay? Now, that's not actually a possible triangle because my third side would just be laying flat and it wouldn't really be a triangle. But anything less, if I cut that angle to something slightly less than 180, anything less than 11 would work. So we say our high-end cutoff is 11. Side length can actually be 11, but it can be anything up to 11, including 10.9, 10.999. That's why we use inequalities instead of just saying it's got to be less. Anyway, that's why we use inequalities, okay? Now, what's the smallest possible third side we could have? Well, if you close the two sides together, if you've got your 4 and you've got your 7, and you make that angle between the 4 and the 7 smaller, you get a smaller third side of your triangle, okay? So again, what's the smallest situation I could create? Well, that's if I create this tiny angle here with a 4 and a 7. And the instant those two things close together, where you've got the 7 and you've got the 4 basically laying on top of it, you could subtract the 2 and you could find out that that missing part would have to be 3, okay? Again, that doesn't actually make a triangle because you just have a 4 and a 3 laying along a 7. And that doesn't make any sense. But anyway, the cutoff can be found by subtracting the two numbers, okay? So x has to be between 3 and 11. And again, the pattern is very simple. Your high-end cutoff is going to be the sum of the two numbers. 4 plus 7 is 11. The low-end cutoff is going to be the difference between the two numbers. 7 minus 4 is equal to 3. So hopefully you can now visualize that as well.